need to note down the running notes carefully. Please need to concentrate the class. Don't mingle with the other operations in your house. Use headphones. It will increases your concentration. And this is our time schedule. If you have any doubt, please post your query in the chat box during the class. Otherwise, raise your hand. And this is our today's outcome. Function generator, square and pulse wave generators. First one is function generator. The second one is square and pulse generator. Function generator, comma, square and pulse wave generator. So up to now we are completed that nothing but this unit is nothing but function generator and different types of function generators. How we are generating different signals using function generators. So up to now we are completed the different signal generators. Like first one is AF fixed signal generator. Second one AF variable signal generator. Third one standard signal generator. Fourth one AF sine wave signal generator. Next one AF square wave signal generator. Next one AF sine by square wave signal generator. So these are the different signal generators. Up to now we are just discussed about a fixed signal generator, AF variable signal generator, standard signal generator. Just go through your running notes. Just go through your running notes. AF sine wave generator, AF square wave generator, and AF sine by square wave signal generator. Nothing but these two waveforms are generated by a single device. So these are the topics up to now we are covered. Just here I am slowly varying those slides from initial to the up to we are covered. Just all of you just go through parallelly with your running notes. So this is signal generator, and this is nothing but signal generator. This is nothing but signal generator. Two types of signal generators, AF fixed and AF variable. These two are the two types of basic types of signal generators. This is nothing but fixed frequency AF oscillator. Fixed frequency, two frequencies, 1 kHz and 400 Hz. Variable frequency, nothing but 20 Hz to 20 kHz. Nothing but audio frequency. That is the range of audio frequency. Of course, this is frequency band limits. Here we have 10 band limits. 10 band limits. Total 10 band limits. Requirements of laboratory type signal generator. This type of signal generator is nothing but variable signal generator. This type of signal generator is nothing but variable signal generator. And these are the different requirements for that. And this is standard signal generator. Very important one. Examination point of view. It's a very important one. Standard signal generator. Important one. So this is something about the explanation for standard signal generator. Next one is advantages of standard signal generator. Disadvantages and applications. This is sine wave generator. Sine wave generator. It's a square wave generator. It's a sine and square wave generator. Sine and square wave generator. Both are combined in one device. This is one device only. This is one device. By using this functional switch, we can vary the we can take the output of sine wave or output of square wave. This is semi trigger, a simple how to convert a sine wave into square wave. So this is the circuit for converting sine wave into square wave. Here we have a wave square wave shaper. So here this square wave shaper is nothing but here we have taken a schematic trigger. So that schematic trigger is available here. And these are the front panel controls, different front panel controls of a sine square wave generator. And this is the description. This is the description about the those front panel controls. And this is our today's task. This is our today's task. All of you please listen this carefully. So here the first one, this is the first block. This is a frequency control network. This frequency control network is nothing but it's an internal one. Nothing but internal source. Internal source. So from that we can vary the frequency using this frequency control. For example, here the frequency is from 0 to 100 kilohertz. So using this network, we can vary the frequencies from 0 to 100 kilohertz using this frequency control. So frequency control network. That means here frequency internally generated and which is controlled and which is varied from the internal source. So that is first one. And see here, if you want to increase the internal frequency ranges, for example, here we have internal frequency is of maximum 100 kilohertz. Later I want to increase it to more than 100 kilohertz, for example, it to 150 kilohertz. Here I am using external source. Here this is nothing but external source. Using this, we can vary external frequency control. So this is internal. As per the internal requirement, it produces. According to the next further conditions, you may require the maximum of compared to the internal. You can add it to the external. Then we may get the maximum from the internal source and which is varied by using this external frequency control. That means this block of this is nothing but source of signal. So this is nothing but source of signal. Here function generator is nothing but that function generator is nothing but which is used to generate three waveforms: sinusoidal, square, and triangle. Of course, in our laboratory also we have a function generator which is used to generate these three types of waveforms. That means which is able to generate these three waveforms simultaneously. So here this first one is the source of signal. Source of signal. Here this signal is nothing but which is used to generate voltage, frequency, phase. Voltage, frequency, phase. Here we have, see here, upper constant current source, lower constant current source. Upper is nothing but actually this is high. Lower is nothing but this is low. This upper is nothing but which is linearly increases with time. And this lower is nothing but linearly decreases with time. Decreases with time. This is nothing but high frequency. And this is nothing but low frequency. If we connected these two, the frequencies are nothing but which is nothing but moderate. We can vary using these upper constant current source and lower constant current source. Upper constant current source is nothing but which is increases the current by varying it, and this lower current constant current source is used to decreases by varying the current. So increases the frequency by increasing the current. Here decreases the frequency by varying the current. Nothing but this is here the frequency is decreased and here the frequency is increased. So here it is nothing but upper. For example, if it is 100 kilohertz, here the maximum is 100 kilohertz, and here this is lower. This is nothing but 0 hertz. And here we are using the same control for increasing and decreasing the frequencies. So upper constant current source is used to increase the frequency with linear, and lower constant current source is used to decrease the frequency in linear. That linear is nothing but the way of increasing, the way of decreasing, both are same. The way of increasing and the way of decreasing both are same. That means these two current sources are used to take the frequencies as constant. The frequencies as constant. That means if you varied a particular frequency, from 1 Hz to 1 kHz, at the middle of the frequency is 500 Hz. Just you fixed that 500 Hz frequency and you are using that 500 frequency to the further circuits. In this condition, there is no variation of its frequency by the current source. That means in that condition of 0 to 1 kHz or 500 Hz, how we are getting that constant? Because of the constant current source only. Because of the constant current source only. If it is you want to increase, use upper constant. If you want to decrease, you can use lower constant. That means just we are varying the frequency. Which is depending upon this constant current sources. If you want to increase, use upper. If you want to decrease, use lower. And these two are connected is nothing but these two are connected. That means in function generator, we are using is a single functional key for increasing and decreasing the frequencies as constant. Increasing and decreasing the frequencies. Of course, by using this frequency control, you can control the frequency, but that controlled frequency is furtherly maintained by this upper constant current sources. This frequency control is used to control the frequency at source level, but at the output level, we can maintain you need to maintain that availed frequency as constant by using some constant current sources. That means these constant current sources are used to maintain the availed frequencies as constant. So this is nothing but the second point. Is it clear? Second point is clear. First point is very simple one. Second point is clear.
Yes, sir.
Thank you. So coming to this integrator, according to the time period and time constant, this integrator converts. Of course, here the frequency is nothing but generated frequency, nothing but it's a sinusoidal signal. It's a sinusoidal signal. Here from this capacitor, here we are taking the sinusoidal signal here. Of course, see here. Here we are taking that sinusoidal signal. So initially here this is sinusoidal signal, and here which is giving to integrator. Integrator is nothing but normal low pass filter. That converts sinusoidal signal into by using T and tau this condition. Condition that converts the sinusoidal signal. This is sinusoidal signal, and this is, and that is triangle. That is triangle. That means here we are giving input of sinusoidal and it produces the output of, see here, it's a triangle. For three requirements we have, one requirement is availed. See here, this is nothing but that triangular waveform. Later, the triangular waveform is applied to voltage comparator multi-vibrator. Voltage comparator multi-vibrator. It's a multi-vibrator, and here that we are giving triangular waveform. It acts as a trigger, and this voltage comparator acts as multi-vibrator, and it produces the square wave. Non-sinusoidal oscillator, simple, it produces the square wave, and which is giving to the amplifier, and square wave is also produced here. So second one is also completed. So coming to this triangular wave is connected to resistance diode shaping circuit. Resistance diode shaping circuit. Resistance diode shaping circuit. Nothing but wave shaping here. So here the circuit is used to, of course, it's a clipper. Of course, it's a clipper. So this is clipped, and this is also clipped. Latter shows like as this is. It's a triangle, and it's a sine. The sine wave is also aware. Sine wave is also aware. So this is, once again, just go through this. I'm giving you one more time. So this is first condition, and this particular block is nothing but source of the signal. This is internal, and this is external. And upper constant current source and lower constant current source. This is high frequency, and this is for low frequency. Both are linear, but here linearly increases, and here linearly decreases. This is integrator, which is used to convert sinusoidal into triangle. The triangle is availed here. Later, this triangular waveform applied to this multi-vibrator. Using this multi-vibrator converts that into square wave. Just here we are using amplifier to increase the strength of the signal. You need to amplify or not, whatever it may be that here. If you want to, there is no amplifications required. You may take output here. Here also. That means in this wave shaping condition, the signal may gets lose some its voltages. So that's why we need to improve that by using a simple amplifier. That's why here we are connecting. If no need to amplify, then you take that signal as directly from this particular block. So here again we are taking that resistance diode shaping network. Simple, it's a clipper. So this clipper is used to clip that particular. Then this is nothing but the output of sinusoidal signal. See here, generally we have defined previously sinusoidal signal and square wave. Here, for example, a triangular. So triangular wave is nothing but, of course, this is look like not so like this. This is triangular. In this triangular waveform, this particular one is nothing but Ts, and this particular time is nothing but Tr. This Ts is nothing but sweep time. Tr is nothing but restoration time. Restoration time. Ts equals to Tr. Then that signal is nothing but triangular wave. Ts is nothing but Tr. That signal is nothing but triangular wave. If Ts is not equals to Tr, that is not triangular wave. It's a simple normal pulse, or normally a generalized signal which is not defined. It's a normalized signal. So this is nothing but a function generator, and this circuit is used to generate three output waveforms of square, triangle, and sinusoidal. Now is it clear? Please note down this diagram. Please note down this diagram. Make it fast.
Sir, voltage comparator output again comes back to upper constant current source.
Because of to get the linearity. Why here we are connecting this? This is because of you need to connect. If you want, you need to connect this to whatever it may be that. This is for to maintain the linearity. Why? Because this is square wave. That square wave is nothing but symmetrical square wave. That symmetrical square wave is nothing but this is V1. Of course, this is V2. Previously also we discussed that V1 equals to V2 and T1 equals to T2. For to get this particular condition, you need to connect it to that. That means here this high frequency is compared to this constant current source. This the main purpose of this constant current source is to maintain the applied sources as constant. So that is because of that only here we are connecting. If there is no need to get the asymmetry, then you need to eliminate that particular. Clear?
Yes, sir.
Make it fast. Completed. So these are the points related to that function generator. Now, any one of you, please go through these points. Any one of you. Any one of you, please go through these points.
Function generator produces different waveforms of adjustable frequency. The common output waveforms are sine, square, and triangular waves. The frequency may be adjusted from a fraction of hertz to several hundred kilohertz, like various outputs of the generator can be made available at the same time. The frequency controlled voltage regulates two current sources. The upper current source supplies constant current to the integrator, whose output voltage increases linearly with time, according to the equation of the output signal voltage. An increase or decrease in the current increases or decreases the slope of the output voltage and hence controls the frequency. The voltage comparator multivibrator changes states at a predetermined maximum level of the integrator output voltage. This change cuts off the upper current supply and switches on the lower current supply. The lower current source supplies a reverse current to the integrator, so that its output decreases linearly with time. When the output reaches a predetermined minimum level, the voltage comparator again changes state and switches on the higher current source. The output of the integrator is a triangular wave, whose frequency is determined by the magnitude of the current supplied by the constant current sources. The comparator output delivers a square wave voltage of the same frequency. The resistance diode network alters the slope of the triangular wave as its amplitude changes and produces a sine wave with less than 1% distortion.
Yeah, okay. So that's it. This is something about the operations of a function generator. So these are the points. You can note down these points in your own languages by just seeing this block diagram. Next one, square and pulse generator. Square and a pulse generator. See here, uh, previously also I'm given this is positive pulse and this is negative pulse. If these two are, that means positive pulse equals to negative pulse, that is nothing but square wave. If these two are not equal, then it's a pulse trine only. Simple, that is the difference between a square and a pulse. Combination of square and pulse generators, sorry, square and pulse is nothing, a square in square, positive and negative are equal, then that is square wave. If those two are not equal, then it's a pulse only. Nothing but here this, for example, this particular signal. This particular signal is not a square wave. This positive pulse is nowhere connected to negative. If this positive pulse is equals to the negative, then this is square wave. The positive characteristics are exactly similar to the negative, but this is positive, this is negative. According to this, we call this as T on. This is nothing but T off. So this pulse width, nothing but T on. Pulse period, nothing but period is nothing but on plus off. So this is nothing but T on, and this is nothing but T on plus. So this is nothing but T on plus T off. So that is nothing but we call that as T. We call that as T. So that is nothing but according to this T on by T. T on by T. We call that as T on by T. If it is nothing but 50%, that is nothing but square wave. See here the duty cycle of a square wave is 50%. If it is not equals to 50%, it's a pulse. So that is, please note down these points. Please note down these points. Completed. See here, it's a square pulse generator. Square pulse generator. Here, constant current source. Constant current source. This is high, nothing but upper. This is nothing but low, nothing but lower. Here we are produced these two. These two. Of course, this signal may avails a sinusoidal signal. And here we are using a schemic trigger. Here we are using a schemic trigger. This schemic trigger is used to produces the square wave, but here this schemic trigger produces the waveform like this. This is T on and this is T off. What is the name of this signal? Is this a square wave?
No, sir.
No. Simple, it's a, this is positive pulse and this is negative pulse. We don't know about the conditions. That's why this is a simple pulse trine. Accordingly, if you are converted this using this capacitor charging discharging condition, the waveform is like this. So again, this is positive and this is negative. But here, this is here also. This one is nowhere connected to the pulse, the square wave. So that's why this nothing but a pulse. Actually, here our intention is to generate square. But according to the circuit concept, here it produced a number of pulses. Here these two pulses. These two are the two pulses. In the third condition, of course, the third pulse is different to the previous two. But in square wave, in third pulse is exactly similar to the first wave. Nothing but this is the first pulse. This is second pulse. So this third pulse is exactly similar to the first pulse here. So this fourth one is exactly similar to this. This is similar to this. But in pulse here, which is nowhere connected. This is one pulse, second pulse, third pulse, fourth pulse, fifth pulse. Nowhere connected those pulses. That type of one is nothing but pulse generator. Note down that. Note down this diagram. So these are the points related to the particular previous. Here we have another circuit, square and pulse generator. Square and pulse generator. See here, and all of you please observe this very carefully. Of course, this one is nearly equals to the previous function generator. See here, first one, the frequency control of what we are generating. The frequency control of what we are generating. You have to generate here and vary the frequency. This is upper constant current source and this is lower constant current source, and these two are connected to one switching circuit. So that switching circuit is helpful for the frequency ranging. Lower and higher frequencies are connected to symmetry. That symmetry is nothing but which is used to maintain the two pulses same. Used to maintain the two pulses, voltages and time periods are same. Nothing but this is positive pulse, this is negative pulse. This positive pulse voltage, negative pulse voltage, positive pulse time period, negative pulse time period. Nothing but the purpose of this symmetry is to maintain or to obtain the square wave, to get the square wave only. So here, up to here clear. This is previously related to that particular clear. This is frequency control used to generate and used to vary the required frequencies. This is upper constant current used to get high frequencies, lower current source used to get lower current, and here decreasing the currents with the time with respect to the current, and here increases with respect to the time. And this is switching circuit used to switch the different frequency conditions. Of course, if you want here we are using a multiplier. Of course, this is also the under process of this switching circuit. Previously also I am given you multiplier is used to not only for the increasing. Multiplier is the process of not only for the increasing. For example, 100 into 10 equals to 1000. Same as that, 100 into 0.1 equals to 10. Here also multiplication and here also multiplication. Of course, the frequency multipliers are used to increase and decreases the frequencies. So this is for such condition. And here we are generated a particular frequency. Here we are generated a particular frequency, and which is giving to this schematic trigger. Schematic trigger which converts sine wave into square wave. Sine wave into square wave. See here. Of course, this schematic trigger produces exactly the square wave. Exactly the square wave. So that's why for that purpose we need to give some synchronizing pulses to synchronizing pulses but not triggering pulses. Why? Because schemic trigger is trigger free circuit. Schemic trigger is a trigger free circuit. That's why here we are giving a synchronizing pulses. See here, this synchronizing pulses, a schemic trigger to in this direction. In this direction. That means which is to this current sources, which is to this current sources. So this is for to maintain the schemic trigger as accurate. This synchronizing pulse or synchronizing circuit is to maintain the schemic trigger as accurate. Of course, the schemic trigger produced here. So from this square, you can vary the output by connecting the different loads of outputs. Different loads of output. Depending upon that load, we can get the different pulses from square wave. Different pulses from square wave. మీరు ఫంక్షన్ జనరేటర్ లో మన ల్యాబ్ లో యూజ్ చేసే ఫంక్షన్ జనరేటర్ లో మీరు అబ్జర్వ్ చేస్తే అక్కడ డీసీ ఆఫ్సెట్ అని ఒక కండిషన్ ఉంటుంది, ఒక బటన్ ఉంటుంది. If you are varying that particular, you may get the square wave into the rectangular. Square wave into the rectangular. Why that square wave gets that rectangular? Because of by varying the load of the waveform. Load of the waveform is nothing but you can vary the constant current sources either at upper or lower. Upper or lower. It changes the duration of the pulses. Automatically, it changes the duration of the pulses. So that's why these two are nothing but used to get that particular. That means these two are nothing but used to get pulse. These two are used to get pulse. And here this is a trigger output. Of course, this is here we are taking that square wave directly. In our function generators also, trigger output thing is availed at the function generator. There we are directly taking the trigger output of that square wave. There is no internal controls or controlled by using the trigger. We can get that directly from the circuit. So you can take it from trigger. If is there any variations of trigger, the trigger means overlapping. That nothing but this is the square wave. Of course, this is somewhat like this, something overlapped. You can vary that either 0. Here we have minus, positive, and this is 0. If we are varying the trigger from 0 to negative or 0 to positive, we may get that trigger free circuit. So this is nothing but the square wave, and this is nothing but the pulse. So directly from these sources we are taking this, and this ramp capacitor is used to take the ramp upper just by here that is represented as dotted. That is nothing but this is ramp, positive ramp, and of course this is negative ramp. If you want, you may adjust this by using this ramp capacitor. Of course, we are not using because of course it's a integrator to ramp signal, but we are not using. That's why this is represented as like this. If you want any non-linearity condition, use this variable capacitors to adjust that internal frequencies. That's why here the capacitor is connected. Of course, this is also not useful. So directly here the frequencies are generated, which is giving to the schemic trigger. From the schemic trigger here directly we are taking the trigger output from this trigger output circuit, and here we are giving the square wave to the two different outputs. One is 600 ohm, another one is 50 ohm. So by varying this output load, you can get the durations of the pulses. You can get some different durations of the pulses. So that is nothing but a pulse, and this is nothing but a square and pulse wave generator. Square and pulse wave generator. Ma, is it clear?
Yes, sir.
Okay, thank you. Please note down this. Actually, our time is up. That's why I'm taking it as little bit speed. Please note down. Please make it fast. I'll show you it on the next class. Thank you all.